Okay, can I do it? Yeah.
And also we have a clip.
Okay. Okay, I think we can get started. Shall we get started? Okay. Can you hear me fine now? Okay, I don't know whether. Okay. We'll see. Maybe I'll use this one. I guess. Okay. Well, good afternoon, everyone. Welcome to the HTAP tutorial. In case you were looking for something else, this is your last morning before you can get out. So I'm Fatma. Pınar and Yuanyu and I, my colleagues, we are going to be covering HTAP today. So let's just get started. So what is HTAP? So HTAP stands for Hybrid Transactional and Analytical System, and the idea is to execute both transactional OLTP-like workloads as well as the analytics and reporting queries in the same system. And here I'm going to, another disclaimer from the beginning, I'm going to use systems in a loose meaning because some of the things we are going to talk about is not going to really be a single system, but more of a solution that has been put together by integrating a bunch of things. So system in the loose sense. So Gartner basically coined the term HTAP. So this is Gartner's definition. So the key point here is you would like to do transactions that contain update statements, inserts, updates, and deletes, and be able to run analytical complex queries within that same transaction and be able to see the data that you have just inserted, your own updates and your recent data within the same transaction. So that's sort of what Gartner, in the Gartner terms, what is deemed true HTAP. But as we are going to see, most of the system we are going to talk about today will not be satisfying that. So let's basically start with remembering what is OLTP and why are these things so different. So OLTP is characterized by single row insert update lookups, and it is you access small amount of data and you do it many times over. So the throughput is important. And in the case of OLAP, your queries are more complex and longer running, so you do smaller number of queries, but they are way more complex, and each single query touches way more data. So scans are the more normal, are more commonly used in the OLAP systems. And this is going to be important as we discuss various approaches to HTAP and what is done and what's not. Okay, so let's start with taking a look. Why HTAP? Why do we need it? Where is this coming from? Okay, actually, step back. So the status quo is we have a separate transactional system which runs the operational business. All the data gets inserted into the OLTP transaction system. And then there's this step called ETL, which is in the extract, transform, load, that moves the data from the transactional system to the analytical system so that you can do analytics and you can do your OLAP and queries. So this model works reasonably well, but the main problem, and the reason there are two separate systems is because they are configured differently, as we just seen. They have different characteristics, different workloads, and you don't want to mix them if you want high throughput for both. Actually, for transactions, it's more about throughput. What did I do? Okay. And for analytics, it is response time. If you want a good performance, you don't want to mix them. And ETL basically introduces this time delay between the two. What's happening over the last couple of years is there's more and more push for more real-time analytics. And this is basically driving this whole generation of new systems where you want to do analytics as soon as the data arrives, and pushing it towards what we call HTAP, where you insert the data into the same system and do your analysis on the same system. And there is this increases the business agility because you can get better business insights from your data as it arrives. And the other important aspect that is driving this trend is we have a lot of new gen applications that have very fast data insertion rates now, as opposed to like how many bank transactions a person does during a day. But if you look into some of the new applications like IoT and mobile, you get a lot of readings from a sensor in a very high frequency. So the data ingestion rates and the requirements for fast insert is increasing with this in the new environment.
So something I'm getting is a subtext from the way you define things, that it's mainly about the transactions and then also analytics as an additional feature, and it's asymmetric, or can it also be symmetric with respect to the significance of the two aspects?
The reason of the asymmetry is I'm following the chronological order. The data needs to get in before it can be analyzed. So I didn't mean it to be asymmetric. So, I mean, you need to get the data in first, but I'm going to explain in a minute, I also want fast OLAP on it. So, moving on. So let's just take a quick timeline, how the things evolved over time. So we started with separate OLTP OLAP systems, and if you look into this the cast of characters, these are traditional SQL databases, and in fact, each one of those support both at the same time, right? If you look into DB2 or Oracle, you can have a OLAP system, a warehouse, but you can have transactions. You can do asset transactions in that system. So the reason I was emphasizing the new applications and was these systems, the OLAP system will not do the transactions very fast and handle high ingestion rates. And the OLTP systems can do analytic queries, but it's not going to do it fast. So that's basically where all this one size doesn't fit all and specialized system came about. And one first wave of this was specialized engines, which basically instead of using the row stores, use the column stores, and a lot of new techniques to speed up the analytics part of the house. So these are databases that mainly do analytics very fast. So for HTAP, coming back to your question, you can start from this and try to add transactions, or you can start from the transactional ones and try to add analytics. Yeah. So in the meantime, I'm showing this as a timeline, but the fact is these are overlapping in the time dimension, really. We also seen a lot of increase in the data volumes and the increase of the NoSQL and the big data. So for the new application, internet applications, and this high ingestion rates, the NoSQL databases was basically the answer for a lot of people. The problem with NoSQL databases was, yes, they did inserts, updates, and all of those fast, but didn't really support SQL and the analytics portion. So now you can also try to see how you can add that to these systems, which is missing. And in that one, what you see is in the NoSQL big data space, there are the NoSQL key value stores that are doing the transaction side, and there are the Hadoop on SQL, we use the term Hadoop on SQL, which is the Hives, Impala, Presto, Big SQL, which does the analytics, but not the transactions. Again, these are two separate solutions in the big data space. And again, overlapping with these two trends was the specialized next generation OLTP systems, which basically which exploits the large main memories and provides really, really fast ingestion and asset and the next generation OLTP systems. Now what's happening is basically the push of all these new technologies that take better advantage of new hardware and new architectures and work on large volumes of data and pushing into HTAP. And these are some examples. Okay. By the way, we are going to make the slides available from the webpage after the conference for those of you. So here's what we are going to do. We would like to start with looking into architectural decision space and explore a couple of dimensions how these solutions differ. And then we are going to have deeper dive into a select set of systems. I'm saying a select because given the 1.5-hour time tutorial, we are not going to be able to cover everything. And this is also going to be a snapshot of the state of the world as we know it today. So there might be things that are going on we didn't know when we prepared the slides. And 3 months down the line, things might evolve. But this is basically how we figured out things as of now. And we are going to conclude with saying, okay, what are the still big problems remaining and how we move forward. Okay, let's start with the dimensions. The first dimension we want to look at is, okay, so OLTP and OLAP, we want to do both in a single system. So the first thing is, some of these things start saying, okay, I have 2 separate engines that specialize in both, and I'm going to provide some sort of a solution that integrates both, either loosely or tightly, and we are going to see examples of both of them. But the important point for this is one engine will be specialized on the OLTP, on the transaction ingestion side, and the other will be specialized for the analytics. And as I said, because these are really 2 separate systems, there will be some loose coupling between them. HBase and Hadoop on SQL is, for example, an example, and we are going to talk about that in some detail. Another example is IBM's DB2 Analytics Accelerator IDAA, We are not going to cover that in detail, so I would like to say a few words about that. So what this one does is the DP2Z provides the transactions OLTP, but its cycles are very precious, and then if you do more on it, you are going to ruin the performance, or throughput performance. So you want to do analytics, you offload the data into Netezza, and this is basically coupled together and provided as an end-to-end solution. So you are going to be able to do your analytics on the Netezza data. This is different than ETLing it out because it's a copy of the data and it's much more frequent and much faster. And it's a complete solution that works together. And then there will be others that kind of provide tighter integration, and we are going to talk about that. And then there's the other end of the spectrum is there's a single engine that does both. And the amount of support or the efficiency of support for both of them will vary. And we are going to go into details about some of the systems, not all of them. One of them that we are not going to talk in detail is in the big data space, Kudu plus Impala. So in the big data space, the transactional inserts updates usually use HBase, which allows the inserts. And then the analytics batch processing side uses HDFS, and neither supports the other. So you cannot really do point lookups or point inserts into HDFS, and you cannot really do fast scans over HBase. So Kudu is sort of a new storage solution that tries to bridge the gap between the two, that allows both inserts as well as columnar storage and fast scans. So that's basically one system that we are not going to go into much detail. But it is a single solution in the big data space. Okay, the other is the storage options. The reason we have this is because in the world of especially moving to the cloud, now you have the query processor and the storage decoupled. So you can have a single query processor operating on the same storage, or you can have one query engines working with multiple different storage options, or you can have multiple engines working on the same storage. So all of those are possible now. That's why we have storage as one of the dimensions. So you could basically use the same storage. Wildfire, which is a research prototype from IBM, uses Parquet, and it uses the same storage for both the ingestion and the analytics side. And there are also solutions that provide separate storage. For example, you'll see that you can use an NoSQL database like Cassandra for your transactional data, and then make a copy of the data into Parquet and store it in HDFS or S3 and do your Spark SQL queries against that. So they will be two separate storage options. And again, the IBM IDAA is two separate because the transactional data is in raw format, goes to DP2Z, and then the analytics goes to Netezza, and using the columnar organization. Okay, so the third one is how the data is organized. One of the things that we have seen is the systems evolution is row stores were good for single row lookups and when you were only interested in updating a single row, but they didn't provide the best performance for large scans and analytics, and for that one, the columnar organization gives you the better alternative. And then the question becomes, if you want to do both, which one you do? And this is where it gets very interesting because, as you'll see in the next slide, there are very interesting combinations and options out there. So let's basically take a look at that. So the raw format is obvious. You can do transactions, you can do analytics, and most of the traditional first-generation systems fall into this space. You do both, but on a raw store, your analytic workload is not going to run as fast. It's not going to give you the fast OLAP. And some of the next-gen HTAP systems also use raw representation. And then the other alternative is using the columnar representation for both. Wildfire is an example, as I just said. It uses Parquet for both the data inserts as well as the analytics. And then there's the hybrid, which kind of makes sense, right? You are doing a hybrid system, so you are going to use a hybrid storage model, or sorry, hybrid data organization. In this one, there are many, many variations how you do the hybrid. So you could basically say for a given table, you choose either row or column. And IBM's DashDB, by the way, IBM DashDB, DB2Blue are similar technologies. DashDB is the cloud version that has some extra on it, so we are not going to distinguish between them. And then you can also mix the format. So this is also very popular. What a lot of the systems do is they have a fast ingestion engine that works in memory, and the data in memory is organized as rows, so you can do inserts and updates very fast. And then they basically move the data from in memory to disk in a columnar organization and enable fast analytics against that columnar organization. And over there, you have the option of allowing data duplication, the same rows, the same piece of data being both in the row and the column representation, or you don't allow the duplication, and that has the following implication. So suppose now your queries come, you have an analytic query coming in and you want to see all your data, and if you don't have the overlap, what you can do is you can basically run the query on the row organized portion and the column organized portion and take the union. But if you have the overlap, then you have the double counting and other problems. And most of the systems actually, if they allow duplicate, then they go to the columnar, which is optimized for the analytics, for the analytical queries. And most of the time, they do the insert into both row and the column. But for analytics, they go to the column only, which means any query doesn't always see the most recent data. So there might be data that is missing. Yes? SQL Server, yes, they have, and I think they are following into the duplication part and they go to the columnar. As far as I know, they do some batching of the rows before pushing it out to the columnar representation. And Oracle in memory does something similar, whereas MemSQL doesn't allow the duplication, and the analytic query goes to both, and the result is aggregated. So as we go through some of the systems in detail, you'll see the implications of that more. Okay, so this is basically a summary, a table summary of what I just told you. The data organization, it's a combination of storage and data organization. Again, you can organize your data in a row representation and store. And these are our orthogonal dimensions that create a huge space of design alternatives. Yes?
Just a quick correction. SAP HANA has mixed format for tables. That's it. Single format.
Okay, so
Without application.
okay, so one of the other things I need to add is most of the systems I also find that they support multiple options, and it's a time variant thing. So the last time we checked, it was the other way. So okay, so now things get interesting, and this is where we have all the fun, the transactional semantics. So everybody talks about asset, but are there alternatives to this? You have either atomicity or not, you may think. But there is always evil in the details. So from the atomicity perspective, what some of the systems do, they do allow atomicity, but they allow updating a single record at a time. So what happens is as soon as you do like an insert, that's an automated commit right after. So as you can imagine, if you do a single record update, it is pretty easy to localize it to a single shard, and you don't really need to worry about 2PC or any other quorum algorithm. That's an easier one to support. But if you allow multiple records to be updated within the same single statement because you can express a set-oriented update, or you can have multiple statements within a single transaction. Then things get more complicated and interesting. So we are going to look into that a little bit. Consistency, so if you, there are really 2 dimensions to consistency. The definition really says a transaction leaves the database in a consistent state. So what does it consist with respect to? So if you don't have any replicas, you're in a single, you need to still satisfy the integrity constraints and triggers. If you are deleting the primary key of a column, all the rows that point to that needs to be cascadedly deleted. So that needs to happen. So there is that aspect to consistency. And if you're in a distributed system, this is where the cap theorem comes into the picture. Now, if you update, all the replicas needs to be in a consistent state. So you see a consistent state wherever you read the data. So that's the other. And isolation, there are 4 levels of isolation. A lot of systems support more than one option. And actually the list goes from most strict to, and it also, do you allow dirty reads or don't? And this will determine how complicated your write protocols and concurrency control will be. And then regarding durability, so a lot of them support snapshot isolation, and most of them do logging. And there are systems which basically use the log as one copy of the data in a distributed setting. So it is log structured storage, and the log becomes one copy of the data, and then you replicate for availability. And the other option is, especially when you have an in-memory database, or now we have really, really large memories, your log is in memory, how do you flush the log to disk to make it durable? Do you do it synchronously or asynchronously? And some systems will give you an option to trade for latency. Okay, so a closer look into atomicity. I think we kind of talked about it a little bit. Single record transactions, most of the key value stores and NoSQL stores will be supporting this option. There are some examples, Cassandra and RuxDB. And on the other hand of the spectrum, where it is way more complicated, all the SQL systems will allow you to do more complicated. And I also need to say another thing. When you are talking about SQL systems, a lot of these inserts are expressed using the SQL semantics, and the interface to the system is through SQL. You have an update statement. Whereas in the NoSQL cases, it is very often that you are not doing it SQL updates. What you are doing is APIs to insert and delete data. You had a question? Yeah, batching is different. Yeah, and in Cassandra also you can do batching, but I'm.
Maybe this is more like single shard versus multiple shards.
Yeah. So the important aspect of this is really, if you do a single shard transaction, then you don't need to worry about any distributed transaction protocols. So that's the real point here. But batching is orthogonal. So a lot of the systems allow batching because then they can do more inserts per second. And for durability, I think we talked, some of the systems give you the option for durability for latency, like MSQL. Do you flash the log to disk synchronously or asynchronously? You can choose. And I think we also covered most of this. Integrity constraints are important, and a lot of the traditional SQL-like systems and the extensions to HTAB of those variations support these integrity constraints and triggers. And a lot of the ones that, I mean, NoSQL or any of the solutions or SQL solutions in the Hadoop environment, they don't really support any of those integrity or consistency constraints. And on the when you go to the distributed transactions and the cap theorem, well, most of these key value stores will give you the weak and eventual consistency, but they also provide alternatives to trade, and we'll talk about that. And isolation, again, we are kind of talking about different levels. I need to say that most systems give you options, like almost all classical databases, you choose your isolation level. Because your applications may tolerate dirty reads or may not. So all of those are sort of give you the ability to choose. I'm going to skip through so that we can go to more interesting parts. The last dimension we are going to look at is the indexing. So as I said, for OLTP, you are doing single row inserts and single row updates and single row lookups. So locating the data fast is important. So most of them always support primary indexes. I mean, primary indexes are kind of always supported. Secondary indexing is a little trickier if you have a distributed system like HBase. It doesn't always support secondary indexes. And then when you look into the indexing type, it's also interesting because some of the systems, B+3s are sort of the accepted norm for indexes. But if you go to some of these in-memory optimized stores, there are better indexes than B+3s that are suited well for in-memory and large caches, L1, L2 caches. And for large-scale data, when the data is mostly append, the LSM organization gives you good performance. So there are also alternatives into this. Okay, so now that we looked into these dimensions, what we are going to do next is we are going to start from the loosely coupled systems and move to tightly coupled to single system in the spectrum of choices, and we are going to start going into the details of systems. So I'll start with one. So this is basically not a single solution, this is a group of solutions, really. It's a typical pattern where you have HBase, basically doing the inserts, and then the data either stays in HBase or there's some sort of a program that moves the data from HBase to HDFS. And what you do is you use one of the SQL and Hadoop options to do the query. So the problem is, the way this works is the HCatalog provides some sort of a mapping from the HBase tables so that you can express these queries and go against HBase tables to do the scans and the lookups. But the main problem is scans over HBase is very slow. Going through the region servers and doing the quorum algorithms, it's a slow read. And we will see that there are solutions out there that have figured out how to read from HBase fast by actually skipping the region server, directly going to H files. But usually the data gets ingested into HBase, and the analytic queries are through the systems. And because HBase reads are, HBase scans are slow, most often the data gets transformed from HBase, which is row organized, into HDFS, into ORC file or Parquet columnar representation, which is what these systems prefer for fast analytics. So that's sort of, okay, oh, this is what I wanted. If we look, this is a very loosely coupled solution where your transactions and OLAP engines are completely separate engines with separate storage options. And the data organization is also separate row and column. It's all this is completely different options. And transaction semantics depends on what you use, but HBase supports quorum consensus. It's a form of a quorum algorithm, so eventual consistency. And the recency, when you do OLAP, you may not always see the last. If you are reading directly from HBase, you see the last data, but then you don't perform very fast. And if you want to do fast and do the scans, then you don't see the recent data. So there is a trade-off. Okay, and for indexing, HBase have the primary key indexes, and there are solutions out there that have. There are a lot of papers that support propose secondary indexes for HBase, but there's not a good solution out there yet. With that, I think I'm gonna hand over to.
Anybody has any questions?
Yeah, any questions so far? Yes. depends on the application, right? If you have like a high ingest heavy or IoT application, you may need I don't know, 1 million transactions per second maybe. But if you're if you are doing something different, you may need 1,000 transactions per second. It's really applications that kind of drive that. There's not a single number that we can argue should be supported by. That's why we have all these different options. Some of those solutions work well if you can tolerate, I don't know, 100 inserts per second.
And for this IoT basically, so this is mostly like append-only workloads.
Yeah. Appends are transactions. When you insert, you do replication, you still need durability and all of those things. But let's take more questions at the end, okay?
Hi, my name is Yuanyuan Tian, and I will look at another example of loosely coupled system. So another example is basic Cassandra plus Spark. So Spark is a popular OLAP engine or a SQL on Hadoop system. And obviously, people start to use it combined with other key value store, and popular one is Cassandra here to do HTAP. So basically, obviously, data is ingested to Cassandra, and it might go through Spark Streaming or Kafka or other streaming system. For ingestion and for analytics, you have actually two options. One option is you use basically a Cassandra connector for Spark. For that, it basically Spark directly access Cassandra data as a separate data source. So this is basically using data source API of Spark SQL. But since data is in Cassandra and you're trying to access data from Cassandra, so it's going to be very slow for complex queries. But the plus is basically you can access the most recent data. The second option basically is to kind of copy the data from Cassandra into Parquet format on HDFS or some other shared storage, and then you can basically use Spark to query the Parquet formatted data much faster. But then the problem is you miss the most recent data. So the transaction semantics here is really depends on what Cassandra provides, and you have multiple options in Cassandra. And the index is only available in Cassandra for basically mostly primary key. And then you use Spark SQL for analytics queries. And one basic plus for integrated into the Spark ecosystems is that you can basically have graph and machine learning analytics as a free in this integrated system. Okay, so next. So this is basically a summary of what we have. So basically you have Spark for analytics, Cassandra for OLTP, and the storage basically Cassandra plus Parquet if you use option 2. If option 1 is, then you just have Cassandra. Data organization, row for Cassandra and column oriented for Parquet, and depends on the options you choose for Cassandra, you have different levels of transaction semantics. The recency, if you're using option 1, you have latest data, but if you use option 2, you have a delay for OLAP. The indexing support, primary key for lookup in Cassandra, no index support for queries. Okay. All right. So now we start to look at the second category, which is tightly integrated systems. So here we still use separate sort of engines for OLAP and OLTP, but they are more tightly integrated. And I will show you why they are tightly integrated. So Splice machine is kind of a system that between the loosely integrated and tightly integrated. It basically provides, It basically provides the HTAP through integrating Derby plus HBase plus Spark. And Derby gives you this, what's going on? Derby gives you this nice SQL interface. And HBase here serves as the storage engine and as well as the OLTP engine. And then HBase and Spark, they are using separate processes and resource management. So they are kind of loose. Okay, so this is an architecture. So what they do is they keep the kind of the parser of Derby, but they modify the Derby's planner and the optimizer so that they can generate plans that are on HBase and Spark, and then replace Derby's storage storage layer with HBase, and also replace Derby's query executor so that based on based on the kind of workload, you either go to HBase for OLTP or you go to Spark for OLAP. And this is Splice Machines cluster management. So these are HBase region servers. So it basically put this Derby parser, planner, and optimizer inside the HBase region server, and use HBase coprocessor to distribute OLTP computation. And independently, you also have Spark cluster, and these are the Spark worker in the same cluster. For query execution, there are some common steps. The first, it all goes through the Derby's parser optimizer and generate bytecode for the query. And then depends on the kind of query. For OLTP, it basically executes OLTP queries from the bytecode using HBase coprocessor. Here, there are some optimization opportunity. You can use block hash or Bloom filter to optimize the data access. And for OLAP, basically, you generate the Spark execution plan, submit the plan with bytecode, and the Spark actually directly access the H files on HDFS. But that doesn't give you the most latest data, but also merge the deltas from the mem store to give you the RDDs back. So in that sense, it does give you the latest data. Does that make sense? Okay. So this is in summary. So for query execution is using Spark, ingestion using HBase, storage option is the same storage, which is HBase, and it's row format only. And in terms of transaction semantics, so there's not a lot of technical documentation on this. And what I could find from their commercial material is that they support full ACID and snapshot isolation. But I would like to take this with a grain of salt. Since I don't really have a lot of technical material to back this up. And recency of OLAP, basically, they can provide up-to-date data. And the indexing support, they have primary index that comes from HBase. Okay. So Snappy Data is another HTAP system that does this kind of tightly integration. It basically integrates Gemfire with Spark. What is Gemfire? Gemfire basically distributing in-memory cache backed by persistent storage. You can think of it as an in-memory OLTP sort of a system. And this integration between these two are basically more tighter than Cassandra plus Spark. You see why this is tighter, and it provides basically unified API. They actually extend the Spark SQL with some of the OLTP functionalities in it. So using their new sort of Spark SQL API, you can basically do both OLTP and OLAP in the same interface. And then they do federated SQL queries between Spark and Gemfire. So given a query, some parts is executing Gemfire and some parts is executing in Spark. And they are using hybrid row-wise and column table storage. But for a single table, you only have one format. It's either a row table or a column table. Their biggest thing is basically approximate query processing. But in this tutorial, since we're focusing on the HTAP aspect, so we're not going to go into the details of this approximate query processing. So this is the sort of unified cluster picture. So they did actually some major surgery to Spark. So if you're, for those who are familiar with Spark, so in Spark you basically have a Spark driver, and then once you have a job that needs to access data in a distributed fashion, you have the Spark executors spawned, and then after the job is done, these executors are basically and they're basically exit. But here, since they want to support OLTP, so they need the Spark executors to be long-running. So they made a change to Spark to have long-running Spark executors. And they will not be shut down even there's a driver failure. And in order to basically have fault tolerance for the driver, they even have a kind of secondary standby for the driver node. And then they're using consensus-based cluster with eager replication to ensure the fault tolerance of the system. And this is for the storage. They're basically merged the Gemfire's memory manager with Spark's block manager. So they're all in the same as the same component now. And inside you can have both column table and row table. Row tables with primary keys are essentially just hash maps. And you can have even a secondary index on these row tables. For column table, they are directly using a Spark's columnar in-memory format. Okay. So for point queries, injers, and updates, they distinguish the type of query. So if it is a low latency point query, they even bypass the scheduler. So because, oh, actually, did I miss something in the previous slide? Okay, yeah, I missed one point. So basically, they use the same partitioner for Gemfire and Spark, and even the Kafka upstreaming source, so that they're using the same partitioner, so the data doesn't need to move across different nodes. So they're all kind of co-partitioned. And therefore, because they have the same partitioner for low latency query, they know exactly which which shard to go to, so they can bypass the scheduler and get the data back. And then for the row tables, they have primary and secondary index support. So for those column tables, if a table is claimed as a column table, they also allow you to do updates, but it's basically done through this delta row buffer. So it's first written into the delta row buffer and then periodically written as new batches to this column table. And it's using a copy and write semantics to ensure the consistency. As for the transactional semantics, it provides two types of, two levels, read committed and repeatable read. So for OLAP queries, a table can be either partitioned or replicated. And they actually did extend the Spark Catalyst optimizer to basically push down some of the queries into Gemfire. So it's kind of federated SQL. And they also add a couple of more rules to allow for collocated joins, since they know those partitioners, so they can actually support collocated joins. They can support star joins with replicated dimension table if one table is replicated. They can make use of the indexes. They basically even merge the results from delta row table and the column table so that you actually get the latest data. So this is the summary. So obviously you're using Spark and Gemfire for the query processing and ingestion, and then there's only one storage engine behind, which is what is the storage? Okay. Yeah, in memory. And then it's backed up by persistent storage. And in terms of the storage organization, it supports column and row table, but no mixed format for a single table. And then two levels of transaction semantics, and OLAP read up-to-date data, primary and secondary index on row tables only, no index on column tables. Okay. So next is Wildfire. It's a research prototype from IBM Research. It's also kind of a tightly coupled system because we're using a wildfire engine for OLTP and Spark for OLAP. And the system can basically support high volume ingest, including updates, efficient analytics on latest data. And one distinguishing feature of Wildfire is basically support HTAP with open format, and which is Parquet format on shared storage. So not only Wildfire can read it, other readers can also access the data on access actually consistent snapshots of data. So that's a kind of a very unique feature of Wildfire. Again, it also supports a unified API. It basically extends a Spark SQL with transaction functionalities. So using the same Spark environment, you can do transactions and as well as OLAP. And it also does federated SQL queries between Spark and the Wildfire engine. So some queries can be pushed onto the engine, and the remaining can be executed in the Spark. And this is the Wildfire architecture. So from the application side, you can do transactions and analytics. And the analytics goes through basically from Spark to Wildfire engine. And we have two types of Wildfire engine. One type is stateful engine. They are basically handle transactions and analytics on the latest data. And then we also have those stateless daemons, or stateless engine daemons, that they basically only do analytics on the older data. And since we're basically all writing to shared file system in an open format, even vanilla Spark can access sort of older snapshots of the data. And if you're using Wildfire, and if your application requires you to read the most recent data, what we do is basically we will use both the stateless daemons as well as the stateful daemons to get the latest data back. And this is a picture of a life cycle in Wildfire. So you have the inserts updates coming to Wildfire, and they are writing to logs, and the logs are in the live zone. So, and then these log data are groomed, periodically groomed into this groomed zone. What does the grooming do? It's basically writes to shared storage. So at this point, you can access the external readers can access the data. What external reader doesn't see is what's in the live zone, but it's only basically 1 second delay. And another responsibility of the groomed zone is basically maintain index, primary index and secondary index. And then we have actually a more elaborate post-grooming process to resolve conflicts in the system. So in Wildfire, all the inserts are considered as upserts. So if you have multiple rows coming in with the same key, the last writer wins. So last value of the key wins. And the conflict resolution is done through this post-grooming process. And also, most of the time, how you want to query the data is very different from how you want to ingest the data. For the data ingestion, we have a sharding mechanism. But for query, you may want to actually query on a different key that is different from your primary key or sharding key. So what we do is we allow you to basically reorganize the data in the shared storage in a different way so that it's basically better for OLAP queries. So that's also done in this post-programming, post-grooming process. And then lastly, this process also maintains index and versioning so that you can go back to you can actually have as-if query. So you want to go back to, a year ago's data. You can, well, probably not a year ago, but 3 months ago's data. You can actually do that. So again, here, so for for people who are using live wildfire, you can basically see the latest data. So we basically provide the H tab here. And then for the external readers, you can read up to the groomed data. That's about a second delay. And then you can also reuse the kind of more optimized snapshot. That's about 10 minutes delay. And if OLAP in wildfire, basically all modification upserts, and we are resolving conflicts using last writer win. We also provide a different option, which is called sync write, that basically give you a higher isolation level. So it basically, once you have the sync write, then all the subsequent read can read what you write. So that's a better isolation level. And then, yeah. So the fast point queries are using primary and secondary index. Really the secret sauce in wildfire, I would say, for fast ingestion and point queries, so it has a really simple commit procedure, very elaborate post-commit procedures. The grooming and the post-grooming are basically the post-commit procedure. And the interface is basically through Spark, so it extends Spark with the OLTP context. It can be used together with other parts of Spark in the same application. For OLAP, the interface is basically, for the interface, we seamlessly extend Spark SQL so that you can even join a wildfire table with a normal Spark table, and apply pushdown analysis for federated SQL. So basically, there are a number of new rules added to the Catalyst optimizer, and it's using data source API for accessing the data from wildfire stateful engines. And another kind of unique feature is that even Spark UDFs can be pushed down to the wildfire engine. So any kind of anonymous UDF you define in Spark can be executed inside the engine. So that's give you a better performance for OLAP. Oops. To query the latest data, if you're going through the wildfire, you can basically get the most recent data by by basically merge the Parquet results from the delta in the log. So this is a summary. So basically, wildfire uses Spark for query processing, and the wildfire engine for OLTP, and the storage option is basically the same storage option. It's a Parquet format. So it's basically a column format on shared file system. And then it provides two levels of transaction semantics, a snapshot isolation with last writer win for conflicts, and the sync write for a higher level of isolation. And you can basically get up-to-date data for OLAP queries, and it supports both primary and secondary index. Okay, so that's all about the tightly coupled system. Now we're basically getting to the single system for HTAP. We'll start with the first one. We'll talk about the IBM-DB, although it's kind of more the traditional, in the traditional database space, but it's a very interesting one. So DB, as Fatima said, is kind of a blue technology, but it's served on cloud. So it's built with IBM Blue technology. So it's a column store optimized for analytics, main memory query processing, operating on uncompressed data, and fine-grained synopsis and late materialization. And it supports transactions and analytics on both row tables and column tables. So again, in DB, when you create a table, you can say this is a row table or this is a column table. But however, it also provides an option. So if you actually have a row table and you want to support fast analytics, you can create a shadow table for the row table. What is a shadow table? It basically is a column or copy of a row table. But it doesn't have to be the whole copy. It can be, you can include all the columns or a subset of the columns, depends on your analytics queries. And it's implemented as a materialized query table that are maintained basically asynchronously. And a query is So here's the interesting part. So since this is a shadow table, we think that it's another copy of the data. Therefore, when you do the OLAP, you may get late data. But they actually have a kind of latency-based algorithm, and based on the actual query, they can decide whether to route the analytic query to the row table or the shadow table. So that way, they can still sort of guarantee you read the latest data. Okay. So this is in summary. So it's a single system. It's just DB2 with blue acceleration technology. Storage option is just the same. Data organization, you have column table and row tables. And DB2 support ACID transactions. So that's what you get from DashDB also. And you can read the up-to-date data for OLAP, and the primary and secondary index are supported. Okay, now I'll hand over to Pinar. Any questions so far? Yes. Yes.
The column part of this system can be at some point basically go to disk, or it's only in memory.
You mean DashDB? It can go to disk. Yeah.
Okay. And is it also distributed, or it's only on a single node?
This is distributed. It's actually on cloud. This is on cloud version of DB2 Blue. Yeah.
Distributed buffer pools flashes to disk, and then there's no more.
It goes through the buffer pool, and when there's no more space, it flashes to disk.
You have a question, yeah? 39? Yes. So sync write is basically it's not automatically that. What we provide is you have a API call called sync write. So if you don't call sync write, what you get is the sort of a snapshot isolation with last writer win, and then you can optionally. So the application have to call the sync write. Then all the previous write will guarantee are synced, and then from then on, all the reads will see the committed write.
So yeah, I mean, in the other case, yeah, you might see, like, if you have network partition, there might be some updates over there that are not yet seen by you, whereas sync write kind of waits for all those things. Yeah.
Yep.
So a slightly provocative question, if I may. The entire motivation for defining an HTAP, this concept of HTAP is wanting to do better than just having a separate system, then ETL, then another separate system for analytics. But you're telling us about the different architectures, but not anything about performance strengths or any kind of benchmarking. Even if the benchmarking is not completely uniform, and then you ask yourself, okay, so I have a bunch of systems, but is it a good idea to even use them over just a traditional database?
So, first of all, we are not going to show you performance numbers. We are not here to tell you go use this system. Well, the goal of this tutorial is just to cover the design space of alternatives. We are just telling you the alternatives. We are not going to go tell you use this one. Having said that, these are all commercial systems. So it's not going to be basically, there's not going to be a single study that can take all of this and do a performance study. So I don't think that's a very realistic expectation.
And also, yeah, coming from a company, also it's not, they are very, it wouldn't be good for us to kind of show such performance numbers and root for one or the other, because these things get misinterpreted very easily. So
This is an academic setting. We are not basically commercially promoting one or the other.
Yeah.
Just covering the design space.
The strengths of points on the design space typically have to do with saying we do X, some kind of setting that this system is fast or useful or better for, even if it's not an exact number, if we're just laying out the points on the design space.
None of those numbers are reliable. How do you want me to report SAP HANA numbers? Those are created
I mean, same thing we do too, so it's not on the
Yeah.
chip, just
I,
Those are very useless numbers.
This is a really long discussion. We could go on.
yeah. All right.
Okay. Yeah, actually, next system is SAP HANA, and it's great that Ismail is here. So if I give you misinformation, he can correct me. So yeah, continuing with the single engine systems. So SAP HANA is like one of the systems that give you two options for storing your tables. You can either have tables that are row-wise or columnar, but like again, this SAP HANA is an in-memory system, so these are kept in memory. So for the columnar side, you do have compression, and this side also have kind of two different layers of storage. Like one is this main store, which is read optimized and immutable, and like this is mostly for older data, whereas for the new data you have the delta store, which is more write optimized, and updates here are of course deletes and inserts, so like you don't have in place updates. And I will talk about indexing for main store later, but like for delta store, you have a more like traditional B tree for efficient lookups and range queries. Now, going forward with the columnar side, so here, of course, one question is how do you merge data from your delta to the main store? So this is handled as a background task, like you can think of it similar to grooming Yuan described for wildfire. So here, when you want to merge, basically the main store, as I said, is immutable. So you like do kind of make a copy of it, add the updates from the delta store to that one, and in the end, like you kind of get a new snapshot for main, and you have another delta version. And this thing, like you can do, you can trigger this based on your like size of RAM and disk. Like it all depends on how much space you have available for your delta. And also depends on your like ingest rate. Like if you don't have so many updates, you wouldn't trigger this so frequently. Also, like this is an operation that is parallelizable for different columns. Now, as for indexes in this design, so you can basically have like a single column index for different columns. Here, what is used is that since the column store side has dictionary compression and that dictionary is sorted, you kind of have an inverted index that that's kind of depends on that dictionary. So whenever you want to look up a key, you can first look at the dictionary and see the dictionary value for that key, and like finding that value, you then go through the inverted index to get the row IDs for that for the rows that has that key. And in the end, you can go check the actual rows and to see like which ones are valid, because for each row you kind of have this validity bitmap like thing that shows like if something is deleted or updated, you will see a 0 there indicating that this row is like no longer valid. And also, as far as I know, the like multi-column keys and indexes are also supported, but I've read that this is not the preferred option because it has a more significant memory footprint. Like the single value one can basically utilize the dictionary compression. Then like some other things about HANA before I like summarize it. It's depend on multi-version concurrency control, and it provides snapshot isolation for reads. And it's the engine is like, I think it's there had been a lot of research and engineering that goes into parallelization of the database operations. So it's not that you just concurrently run queries, but you also have different techniques of having intra-query parallelism, or for each operator within operators you have different parallelism opportunities, and underneath you can also exploit the parallelism given from the hardware side, like SIMD, utilizing SIMD techniques. And yeah, just to summarize, so again, in HANA you have a single engine, that is HANA, and like it's in memory optimized, but of course like they have persistent through like secondary storage, and they provide two data formats, like row-wise, if you want, like if you have more tables that are used for OLTP, you would want them in row format, whereas the engine is mostly optimized for the columnar format though, and that is more for OLAP and the HTAP portion of things. And for transactions, like it's like mostly an ACID system, but as far as I know, the snapshot isolation is the highest level of isolation. And also like data recency, you can access the latest data because you have like one engine, and there is no like, even though you have Delta Store, you have access to Delta Store easily in that engine. And the indexing support, you have both like primary and secondary indexes, and whereas like the row store side, so the Delta Store we said has a B+3 index, but the more read optimized side, the columnar side, has this inverted index that is based on the dictionary. Now the next system I will detail is MemSQL. And like similar to HANA, MemSQL also gives you two options to store tables. Like you can either use the row store to keep a table, or the column store. Now the row store size, like that's strictly kept in memory. If your data fits in memory, like you can just use the row store for both OLTP and OLAP and have operational analytics in there. But like in most cases, for most HTAP applications out there, usually data is big, so it wouldn't fit in memory. So therefore, they also have the option of this column storage. And here again, you can have data ingestion via either inserts and updates, and handle both OLTP and OLAP on this store. Now, when MemSQL first came out, like the main thing behind its design was this skip list structure that they developed. So its row store portion, especially, it heavily relies on skip lists, and it's basically an in-memory optimized data structure. It has a very lean code base, so your lookup statement don't end up in a huge instruction footprint like it would in a traditional B tree, and it can also be accessed in a large-free fashion. And it has like basically time complexity-wise, like log and lookup, inserts, updates, and so on. But it's like, again, it's kept in memory, like nothing in the row store side in MemSQL is persisted. But of course, like they have, it's not like they don't have durability. They have periodic snapshots, and they have logging which is by default asynchronous, but you can also, like they give you the option to enable synchronous logging as well. So you get durability that way. But when you restart your system, basically, even though your data is there, your skip list indexes wouldn't be there, so that needs to be rebuilt. Also, they have support for like latch-free hash tables and geospatial indexes as well. Now, for the column store side, they kind of have a log structure merge tree like design here. So tables are they are stored like a clustered index. So like you would have some columns, like you would pick some columns as the keys, and things would be ordered based on that key. So here, like in this picture, like each of these rectangles, it's called a row segment. So it basically keeps rows in kind of PAX format, like you would have all the columns for that row in that row segment, but things are kept columnar within that row segment. And again, different row segment, they keep different data ranges, so they are not overlapped, but like in the background you have a merge process for like you would have in a log structured merge tree architecture. And the operations on this column store is that the ingest, like if you have small batch ingest, it's usually not efficient to do such things on a column store, so they use the row store code base for this, like even though the data structure underneath is still row segments. If you have a large batch, it directly goes to the column store portion. And again, in the background, these two portions are merged periodically. Reads at the column store side served by snapshot isolation. But I should make something clear there. So at the row store side, like the transactions that go there, it has read committed isolation. So it's kind of weaker than snapshots. And again, deletes are more like the deletes are served as tombstones, so you don't do like in-place deletes, similar to updates. Like updates are delete and insert, like it was in HANA. And also the overall architecture for their distributed setting is that you have, it's kind of similar to MapReduce like design. So you have aggregators and leaves. The aggregators kind of receive the requests and routes them to proper leaf nodes. Leaf nodes store the data, handle, execute the request, and then basically send the results back to aggregators, which aggregate the results before sending them to user. Data is partitioned across different nodes. And the intermediary results, again, they are treated like Spark's RDDs. They also have efficient query compilation using LLVM, and like they can basically cache some of the compiled queries. Like if they are frequently asked in the system, they don't have to compile them over and over. And as time goes by, they also kind of improve some of the code paths within hot queries. And also, like another option for like MemSQL, if you want to use it for HTAP, is that they also have a Spark connector, which kind of you might be accessing the data with more latency because it's no longer the single engine anymore. So to quickly summarize MemSQL as well, so you have, again, one engine. It's both in memory and SSD optimized. And data organization-wise, you have both options. Like you can either keep the tables as in a row format or columnar format. and transactional semantics wise, like I would say memSQL is a bit more loose when it comes to ACID, like because by default they give you asynchronous logging, or the transactions are handled in like in read committed isolation level. And I mean, they actually follow, so from the columnar side, I mean, it might take data to be transferred to the columnar side a bit, but they also give you the option of like joining the row side and column side, so you can actually access the up-to-date data. And we said, like, for indexing support, I would say skip lists are the kind of the heavily used index for the row store size, and they have a more LSM-like structure for the columnar side. And the last system I will talk about is Hyper, which, like, unlike the other systems we talked in this category, it originally came from academia, from TU Munich. So the goal was like doing OLTP on OLAP requests in one engine. Hyper like changed a lot over the years, but like today, like initially it just it was just a row store, but today they provide a columnar engine as well. You just need to pick it like upfront whether you want to use the columnar engine or row engine. So you cannot have some tables in row formats or some tables in column format. It's also heavily optimized for in memory processing. It supports serializable multi-version concurrency control, and it also has query compilation using LLVM, and like they really generate really efficient code paths by doing that. Their instruction footprint is really low. From the indexing side, they use adaptive radix tree, which is these are all, by the way, based on several research projects that come from TU Munich. So in the version of the slides we post online, I will put the references for the papers there. But basically, based on the adaptive radix tree paper, like they have comparable performance to a hash-based tree, but they also enable range scans. And also, like they had research on NUMA-aware joins or compaction of all data, since like it's a system that is based on in-memory processing. You need to really effectively compact all data so you can more efficiently use your memory resources. And yeah, this is just a quick summary of Hyper as well, which just summarizes what I've said so far. So before I conclude in the next 2-3 minutes, do you have any questions about the systems I described?
Yes.
Mm-hmm.
About the Hyper, so
Mm-hmm.
the row store and the column store is fixed at the beginning. Can they change on the fly?
I mean, as far as I know, no. I mean, I don't know if they have a process, like a bulk process that would convert data from one format to the other. I am not aware of that. Yeah.
And another question is like, when are those row stores are transformed to column stores, like in HANA or memory SQL? They do it periodically or when they have some threshold?
So for memSQL, yeah, I mean, they have this, like, they kind of treat it like LSM, so they have a periodic background process. For HANA, I'm less sure. Maybe Ismail can answer
Sure.
that.
Actually, delta parts, the dynamic part, so the right part size. So it's a sort of like a percentage of the total size of the database. So since you want to retain good OLAP performance, you don't want your raw store part to grow big. So whenever you reach certain threshold, you merge it with the main. So it depends on your write rate.
So delta part is then raw in raw format, you are saying, because okay.
So if it is update only, the data is always in raw format, right? If there's
Yes, it's in the raw format.
so it's if there's no insert, it's just only.
No, in fact, what you do is once you merge it, you start a new empty delta.
Yeah, there is.
Yes, but what if it is only update only? If the workload is update only.
So in a way, do you have in place updates in the Delta store?
In the Delta store, I think it's MVCC with garbage collection.
Okay, so
it's sort of you survive. So if you have updates with garbage collection, so you retain the same size. So it would still.
yeah, okay, yeah. If you mostly have updates, then if your memory wouldn't be, if you have proper garbage collection, then maybe you can keep it longer.
I do not see the requirement for merging because if it's update only workload, why do you need merge the delta to?
No, you merge the delta only when the delta reaches a certain threshold,
Threshold,
size.
yeah.
Yes.
So if you only have updates and if it doesn't reach that side, then it wouldn't be merged. Yeah. Yeah. And okay, yeah. So in the next 2-3 minutes, I would conclude very briefly. So first, like we have described various systems claiming that they do HTAP. So what are the outstanding challenges here? So one thing is that like even though again we showed all these systems that were supposed to be HTAP systems, none of them are actually true HTAP depending on Gartner's definition of HTAP, because Gartner says that you need to be able to run queries, ideally complex queries within transactions that potentially has updates. Whereas like all these systems, they kind of have a transaction optimized part and query optimized part, and is kind of queries have ability to access almost latest data, but they are not optimized for running queries in a transaction. So that part is still a challenge, and that's not really solved yet. The other thing is, again, except for the last batch of systems, the others depend on maintaining different systems while giving the illusion to the user that they have one system they are interacting with. But again, these different components, sometimes they are maintained by a completely different group. Like in the case of Spark-based architectures, Spark keep releasing different versions all the time. Like how do you maintain that system while keeping the up-to-date properties of another system maintained by a completely different group. The other thing is now the last two things I will talk about, like it's not maybe just HTAP related problems, but it also comes because of the distributed or large scale characteristic of these systems. One is that like indexing, okay, we saw options for different options for indexing, but if you have a system that keeps data in Parquet format on a shared file system or on an object store, like doing efficient access to these things is still not that possible, especially if you want like point lookups with low latency. This is again not a solved issue yet. And the other thing is like effective caching. Again, this is related to low latency lookups. Like if you have data in Parquet on HDFS, you wouldn't have low latency lookup. So these are things that we still need to work on. And finally, just to briefly summarize what we have seen, so we know that traditionally systems are optimized. So one type of request, like either for transactional on OLAP, that's why we have all these in-memory optimized row stores and column stores. But there are many new applications that basically drive the need for a system that can handle both of these types of requests in a single system. And we also need to enable that at a large scale in like either cloud deployments or a private distributed setting. Today, many approaches that trying to handle this new age HTAP applications is they can either choose a design that have a single system handling both type of requests, or they can be utilizing multiple systems underneath, even though they give the user an illusion of a single system. And they might be supporting different data formats underneath, again, either for different tables or even for the same table. And basically, depending on this design space, they provide you with different transactional guarantees and recency guarantees. So depending on your needs, like you can pick one or the other depending on what they can give you in terms of transactions and recency. So with that, I will conclude, and we'll be happy to take any other questions you might have. Okay.
So I have a question about the wildfire system. So in that system, you mentioned that in the 10 minutes grooming process, there can be a conflict resolution. So does that mean during that process, some of the updates can be aborted?
No, we still, so we still allow updates. The thing is, like, they will kind of go to this site,
Yes.
whereas you do that conflict resolution here. So this kind of gets everything.
Yeah, but when do you like?
So I guess the confusion is the last write to read versus
Yeah,
first write
yeah.
to read. It's not that any transaction gets aborted at that time.
Okay.
I have to say, all the modifications are abstract. So basically, you just similar like key value store. You have the key and the value, and the last key and value wins.
Oh, so basically you mean override? Okay.
Yeah. So it's not aborted, yeah.
No, but actually the question is it possible that the previous value has been seen by another transaction? So what do you mean last write means? So is there a point where there is another write and then another write and then another write? Somebody can see any of them or just the last one?
So yeah, it depends on when that read happens. Like, we provide that with snapshot isolation. So depending on the start time of the query, you see the last write based on that, based on your start time.
Any of them, right?
Yeah, but it's based on your start time again. You will see the latest at the time of the, yeah.
But that's not a snapshot isolation, right? Because in standard snapshot isolation, you cannot see multiple writes.
No, you don't see the multiple values. You still see the latest one.
Uh,
Or do you read uncommitted?
No, latest committed.
So I think the last writer wins is like conflict. You decide which one wins. Then it's the
Yeah.
I guess another problem is that, but for the OLTP part, is that distributed? Or is
Yeah,
it
it's
single?
distributed. I think Darko had a question.
So when I think at least about OLTP and OLAP, then for OLAP, first thing I think is TPCH, and I think most of the systems can run TPCH to a certain extent. But when I think of OLTP, I think of TPCC. Now, some of the systems, especially like edge-based systems, cannot run TPCC. So, can you draw a boundary between, which systems are hybrid transaction analytical processing based on whether they can run a certain workload?
Yeah, so like that again depends on whether they support like multi-statement transactions or not. And I mean, you are right, like the more the systems that like handle, that are like single engine systems, most of them are designed in a way that they support multi-statement transactions like the ones in TPCC, but like the ones, I guess like Wildfire is also currently an example for that, like they just have single statement transactions.
The other aspect of this, some of those systems don't even have a SQL interface. So they only have a bunch of APIs for inserts. They don't necessarily support the SQL statements. And SQL has not just insert update, it also has upserts and more sophisticated statements. And most of these key value stores don't really support any of them. But they have the ability to ingest data. So that's why in the slides even we use the transactions and ingestion sort of interchangeably.
I think as a follow-up question, the main problem is that we don't have a clearly defined workload for the hybrid HTAP workloads, right? So because
workload, we don't have a benchmark.
yes, I mean we don't have the benchmark so that we can clearly distinguish between the systems and say which ones are the ones that support what the users actually need. And what Gartner defines, I mean, we were using the CH benchmark, but even that one we had to modify so that the schema of TPCH is not skewed by the type of timestamp transactions that TPCC has. So, and then of course the more complex queries that we're talking about are not captured by anything that we have out there. So maybe as a community we should first do that, right? And then we start evaluating the systems. I mean, probably it should start from you the enterprise companies that have access to what the clients actually need.
So I wouldn't say we don't have workloads, but I would say we don't have a benchmark. I just want to be clear about workload versus benchmark because there's real need for the systems, customer demand that is driving the evolution of the systems. There are workloads out there, it's just that we don't have a well-defined TPC, whatever X benchmark to evaluate them.
Yeah, I mean, it's not, yes, it's the benchmark because we need not just the workload to run it, but also on what exactly the user expects from it in terms of the latencies, the data freshness, the predictability of the system, and so on. So there are so many dimensions in that.
So
But the problem is that different workloads you see from different users, they really have different
Requirements, yeah.
some of the systems are basically really have the high volume ingestion and it's append only. They don't really need the TPCE, supporting TPCE. So doing that is not going to be very meaningful.
Yeah.
So,
but some on the other hand, like fraud detection, whatever, they do need complex transactions again.
Yeah.
So it's also hard to define a benchmark.
But
and
I don't want to discard the suggestion. I think it is important to have some sort of a benchmark or a suite of things that you can basically at least define some clear criteria how to basically look into data recency, strictness of the transaction. Some of those I agree that there's still some empty space that needs to be defined, and yes, this community can help with that space.
So there is actually the TPCH benchmark, but it actually covers only sort of enterprise-like workloads.
TPCH only does analytics. It has insert, but it isn't meant to do the like TPCE like inserts and lookups.
Yeah.
So there's not a single TPC benchmark that has a good combination.
I think HTAP systems are not like a single class of systems.
No.
I think it's multiple classes of systems. And I think that's the misleading part. Yeah. We would need a separate benchmark for every use case.
We need a suite of benchmarks maybe because the use cases are more complicated because the solutions of but we look at today's enterprises, the solutions and the whole data architecture is very complicated.
I mean, looking at the heterogeneity of the systems, would you conclude that no size fits all? One span for all?
I would say yes, because depends on the application requirements. Some applications that really don't need to query the latest data, and then for them, a very loosely coupled system is good enough, and they're happy with that. And others, they really require to query the latest data, and for that, you need either tightly integrated or one single system.
So one dimension we haven't really touched, and that probably should be taken into account, is the manageability, right? If you have a tightly coupled system, it's one system that you need to deal with, and you don't need to worry about, it's self-managing, it's easier. So if you are managing a bunch of different systems, then the management and running of that becomes an issue too. So we haven't really talked about any of those aspects. But if you have a solution and you want to make that available on the web, you need to worry about deploying it, running it, maintaining it, all of that basically. That's why there is not a single solution. There's spectrum of problems, and there's a solution for each different problem.
And some of them do offer cloud-based service, and for that, the manageability is basically offload to the cloud, like a DashDB or
to the other side.
Yeah.
So basically, you mentioned that your system Wildfire fits perfectly for this IoT workload. So, for example,
Say that?
No, we never say it's perfectly. It's one of the systems. It's definitely our favorite.
It's a research prototype.
Yeah.
By definition, a research prototype is not a perfect fit for a real-world problem.
anyway, so the question is more about so Wildfire is, let's say that you focus on IoT workload, let's say, and then, for example, you also mentioned workload, something like fraud detection, which seems to be one of the best examples for HTAP system. And then my question is, through all of these examples, we went through many systems, and then maybe you could just, let's say, identify a system that can efficiently support this workload for fraud detection. For example, your system like DashDB, does it support this fraud detection effectively or not? Or maybe you could recommend other system that really supports this kind of, I would say probably one of the most challenging HTAP workloads.
I mean, fraud detection is also a very big field. It depends on the actual workload.
So I don't think you can basically create a table where it says, okay, fraud detection, and these systems can support and this not. That table will be very difficult to create. So as she just said, fraud detection
So for example,
is not a single application. It's kind of has many colors to it. And some of the systems, as we kept emphasizing, support many options. Like Cassandra supports different transaction semantics. You basically, with the right tweaks and the right screws, some of them can be made to support it. So if I publish a table that says it doesn't support it, the vendor will really get mad at me and say, no, if you do this setup, it will. So that's why it is very, what we can do, and I think that's a good suggestion is when we basically do the follow-up to this, we can basically say these are, for these type of applications, I don't think we can say this single application, these things do. We can basically say these systems have the potential for supporting it, but I don't think we can make I don't think it is fair to make that type of concrete claims because we are not doing marketing for any of the systems. Okay, so one of the things, for example, would be fair to say if you have a high data ingestion, like an IoT application that requires 1 million inserts per second, something like HBase may not be able to keep up with it. We could make those statements. But we will not be able to say, okay, DashDB will be able to support fraud detection, but HBase cannot. I think it's a little stretch to go that far.
So you mentioned there are different requirements for different workloads in terms of the freshness of the data. So one thing I would like to know about is that could you give us some examples of the applications that require data freshness under like sub-minute, like under 1 minute?
Fraud detection.
Fraud detection.
But I would say, like, if you do fraud detection, it takes more than a minute for our human to react to some of.
No,
No,
you want to
those are-
see what's happening as soon as it's happening, because there's other heavy algorithms that need to run it to figure out it is fraud and the reaction time. But you want to know, you want to have access to data as soon as possible.
But does it really matter, like, for 1 minute versus like a 10-minute react time?
I think it matters. Those are money involved.
I mean, not for our money probably, but like Donald Trump's money, it would matter.
Why not use streaming computing, right?
What? Computing.
Why not use streaming system to do?
So streaming systems also have limited capability for a query, because they don't really go to all the historical data. They do windowing. They don't really do the full thing. They have their limits. So one last question, and I think we need to wrap up. Okay. Thank you for coming.
Thank you.